here's what will blow your mind right from the start. If you left Earth right now on the fastest spacecraft humans have ever built, NASA's Parker Solar Probe, traveling at 430,000 miles per hour, it would take you 225 million years just to cross the Milky Way. That's not a typo. 225 million years. To put that in perspective, modern humans have only existed for about 300,000 years. You would need to survive for 750 times longer than our entire species has even existed just to drive across our galaxy. But here's where it gets even crazier. That's assuming you somehow never slowed down, faced zero obstacles, and could maintain that velocity through the infinite vacuum of space. In reality, the true answer is so much more mind-bending than that number. And by the end of this video, you're going to understand not just how long it would take, but why that distance is so incomprehensibly vast that it breaks our brains. Before we dive into this cosmic journey, I have to ask, where are you watching this from? Drop your country and the time you're watching in the comments right now. I read every single comment, and I genuinely love connecting with you across the globe. And if you haven't already, please subscribe and hit that notification bell. I upload new mind-bending content like this every single week, and you won't want to miss what's coming. Because here's the thing, understanding galactic scale isn't just about numbers. It's about fundamentally restructuring how you see your place in the universe. By the time we're done here, you're going to feel simultaneously smaller and more profound than you've ever felt before. And that feeling, that cognitive shift, that's what this video is really about. So let's start with the absolute basics, but I promise you, we're going to twist everything you think you know. Before we can understand how long it takes to cross our galaxy, we need to understand what we're actually crossing. The Milky Way isn't just a random collection of stars floating in space. It's a massive rotating disk of stars, gas, dust, and dark matter held together by gravity, and it's absolutely enormous. Let me start with something most people don't realize. The name Milky Way comes from how it looks from Earth. When you see that hazy band of light stretching across the night sky, it looks like milk spilled across the heavens. Ancient astronomers didn't know what it actually was. They thought maybe it was just an atmospheric phenomenon. It wasn't until the 1920s that Edwin Hubble, yes, that Hubble, the one the telescope is named after, actually proved that the Milky Way was a separate galaxy containing billions of stars. Before that, we genuinely didn't know we lived in a galaxy. Think of it like this. Imagine you're a single cell inside a massive organism, and for thousands of years, humans only see the cell wall around them. Then suddenly, in 1924, a scientist named Hubble points a telescope at a specific region and reveals the entire body of living inside. That's what discovering the true nature of the Milky Way felt like. It was revolutionary. Now, here's the shape of the Milky Way that's fascinating. It's a spiral galaxy. And when I say spiral, I don't mean a tight little tornado. I mean a vast, rotating disk with massive spiral arms. Our Sun with Earth and our entire solar system sits about 26,000 light years from the galactic center. That's already a massive distance, but it's nowhere near the outer edge of the galaxy. Think of it like being on a spinning record. You're not at the center, you're not at the edge, you're somewhere in the middle rings, going around and around with everything else. The entire Milky Way is approximately 100,000 light years in diameter. Now, a light year is the distance light travels in 1 year, about 5.88 trillion miles. Let me put that in perspective. Light is the fastest thing in the universe. Nothing with mass can travel faster than light. And it takes light 100,000 years to cross from one side of our galaxy to the other. That's how impossibly vast this is. Here's your first mind-blown moment. The photons coming to your eyes from distant stars in the Milky Way left those stars before your ancestors developed agriculture, before writing was invented, before civilization existed. The light is ancient, and the distance is incomprehensible. But wait, we need to complicate this even more, because here's what's really fascinating about galactic structure. The Milky Way isn't evenly distributed. It's denser in some areas, sparse in others. The galactic center is packed with billions of stars, swirling around what scientists discovered in 2020, a supermassive black hole called Sagittarius A*, which contains about 4 million times the mass of our Sun. That's Reinhard Genzel and Andrea Gheze's Nobel Prize-winning discovery. They spent decades tracking individual stars orbiting this black hole to prove it existed, finally confirming it through gravitational effects we could actually measure. And here's the cognitive dissonance. Our entire galaxy is rotating around this incredibly dense center of gravity. We're all spiraling slowly around a black hole. You're on a planet that's spiraling around a star that's spiraling around a black hole. Nested chaos. Beautiful nested chaos. Now, when we talk about crossing the galaxy, we're essentially talking about traversing from one edge to the opposite edge covering that 100,000 light-year span. But the real question becomes, what path do we take? Do we go straight through? Do we follow the spiral? Do we climb out of the galactic plane? This is where the real complexity begins, and this is exactly where most people get it wrong. Okay, so most people think the challenge of crossing the galaxy is purely about distance. It's not even close. In fact, distance is just one layer of a much more complex problem, and understanding this layer is crucial before we get to the real mind-benders. Let me introduce you to the cosmic environment you'd be traveling through. It's not the empty void people imagine. The space between stars contains what's called the interstellar medium, a thin but real combination of gas, dust, and radiation. Think of it like this. Imagine trying to drive across an ocean. The ocean is mostly water, but there are currents, there are waves, there are particles suspended throughout. Space is similar, just infinitely more sparse. But it's not nothing. The interstellar medium contains regions of extreme variation. Some areas are almost pure vacuum, what we call hot ionized medium. Other areas are dense molecular clouds regions so thick with dust and gas that visible light literally cannot penetrate them. We have to use infrared and radio telescopes to see through. These molecular clouds are actually where stars are born. They're not obstacles to avoid. They're the cosmic nurseries of the universe. Here's a fact that will reshape how you think about travel. Voyager 1, the fastest human spacecraft, is traveling at about 38,000 miles per hour. It left our solar system in 2012. In 300 years, it will still be 1.6 light years away from the nearest star. Not because it's slow, but because space is so incomprehensibly vast that even our fastest achievement feels glacial against the cosmic scale. Think of it like this. If Earth were the size of a marble, the nearest star would be about 4 miles away. Now, if Voyager 1 were a grain of sand moving at that marble scale, it would take about 80,000 years to reach that other marble. And that's just one star. Now imagine that marble Earth is only one point in a galaxy containing 100 to 200 billion stars spread across 100,000 light years. Your brain should be starting to break a little right now. But here's the second mind-blown moment. The Parker Solar Probe. I mentioned at the beginning that 430,000 miles per hour spacecraft, it's not actually moving through open space at that speed. It achieved that velocity by using the sun's gravity to accelerate it. Once it's away from our star, it's traveling much slower through open space. And here's the kicker. Even at its peak velocity, if the Parker Solar Probe were aimed at the nearest star system, Alpha Centauri, which is only 4.37 light years away, it would take about 78,000 years to get there. Let me repeat that. 78,000 years to reach our nearest star neighbor. That's incomprehensibly long. And now we need to add another layer. What about relativistic effects? This is where physics gets weird. And this is where most people don't understand what's really stopping us from crossing the galaxy. At velocities approaching the speed of light, which we cannot achieve with current physics, time dilation becomes a real factor. According to Einstein's special relativity, as you accelerate closer to the speed of light, time literally slows down for you relative to the rest of the universe. This isn't science fiction. This is Einstein's 1905 groundbreaking paper that revolutionized physics. This is real. Think of it like this. Imagine you're traveling at 99.9% the speed of light toward Alpha Centauri. From Earth's perspective, you're taking 4.4 years to get there. But from your perspective, because of time dilation, the journey might only feel like a few months. You would experience aging very slowly, while everyone on Earth aged rapidly. This is the only theoretical loophole to crossing vast distances. You don't actually experience the time passing as fast. But here's the problem. We have no technology and no known physics that would allow us to accelerate a spacecraft to near light speeds. The energy requirements are absolutely astronomical. A spacecraft with even a modest mass of 1,000 kilograms, accelerated to just 10% the speed of light, would require energy equivalent to the total annual energy consumption of the entire human civilization. This is where we hit the edge of what's theoretically possible with known physics. So let's actually categorize how long it would take under different technological scenarios. This is crucial because the answer changes dramatically depending on what level of technology we're discussing. First, current technology. Today, right now, with spacecraft like New Horizons, Voyager 1, and the Parker Solar Probe, the fastest we can push a spacecraft to is around 120 miles per second, about 430,000 miles per hour. The Parker Solar Probe holds the record. At this speed, crossing the galaxy would take approximately 225 to 250 million years. That's longer than dinosaurs ruled the Earth. All of that history, 130 million years of dinosaurs, and you'd still have another 120 million years to go. Now, when physicists get serious about interstellar travel, they usually start talking about theoretical propulsion systems. Let me introduce you to three major concepts. The first is the ion drive. NASA has been experimenting with ion drives since the 1990s. An ion drive works by ionizing propellant, usually a noble gas like xenon, and accelerating those charged particles through electromagnetic fields. The advantage is incredible fuel efficiency. The disadvantage is they produce very low thrust. An ion drive could theoretically accelerate a spacecraft to about 50 to 100 kilometers per second, much faster than conventional rockets. At that speed, crossing the galaxy would take about 1 to 2 billion years. Still incomprehensible, but incrementally better. The second theoretical system is nuclear fusion drives. Instead of chemical reactions like we use today, a fusion drive would harness the power of fusing hydrogen nuclei into helium, the same process, powering the sun. Theoretical physicists like Stephen Hawking have discussed how fusion drives could theoretically achieve 30% the speed of light. That would reduce galactic crossing time to about 300,000 years. That's still longer than our species has existed, but it's starting to become less insane. Think of it like this. If galactic crossing with current tech is like walking to the moon, fusion drives would be like flying there. Much faster, but you're still talking about a journey measured in civilizational timescales, not human lifetimes. The third, and this is where we get into pure speculation, is the concept of an Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. The Alcubierre drive would theoretically warp spacetime itself, creating a bubble of normal space inside a bubble of warped space. You wouldn't be traveling through space. You'd be traveling with space. Mathematically, this doesn't violate Einstein's equations. It's theoretically possible. Here's the catch that's absolutely brutal. Building an Alcubierre drive would require negative energy specifically, exotic matter with negative mass. We've never observed negative mass. We don't know if it exists. We don't know how to create it. And if it does exist, we'd need an amount of exotic matter roughly equivalent to the mass of Jupiter, just to warp a small area of spacetime. So it's theoretically possible, but practically impossible with any foreseeable technology. But here's a mind-blown moment that will stick with you. The Alcubierre drive wouldn't actually violate causality or create time travel paradoxes if the exotic matter required were real. It would just bend the rules of space, not time. It would be genuinely revolutionary physics, but still bound by the universe's laws. Multiple physicists, including Sean Carroll and Kip Thorne, have studied this seriously. This isn't fringe science. It's speculative physics from credible scientists. Now, let's get even more speculative. Some physicists have proposed the concept of wormholes, Einstein-Rosen bridges, as shortcuts through spacetime. If you could create a stable wormhole connecting two distant points in space, you could theoretically cross the galaxy almost instantly. But again, the problems. We don't know if stable wormholes can exist. We don't know how to create one. And many physicists suspect that any wormhole you could theoretically create would collapse instantly under any mass trying to pass through it. This is Carl Sagan territory. Even Sagan, when writing Contact, had to invoke advanced alien technology to make wormholes work. That should tell you something about how speculative this is. So here's the honest truth. With known physics and achievable technology, crossing the galaxy takes a civilizational scale time frame. With theoretical physics we can't build yet. It might take slightly less, but we're still talking about thousands or millions of years for most scenarios. The question isn't really how long anymore. It's why would we ever try? Before we can truly understand galactic crossing, we need to acknowledge that human brains literally didn't evolve to comprehend these scales. This isn't hyperbole. Our brains evolved to deal with distances measured in meters to kilometers, timescales measured in seconds to decades, and objects we could see and touch. When you try to comprehend cosmic scales, you're trying to do something your neurology is not equipped for. Your brain will lie to you. It will say it understands 100,000 light years, but it doesn't. Not really. Not intuitively. This is cognitive dissonance at its deepest level. Let me try a progression of analogies to help your brain actually feel these scales. Imagine our solar system as a dinner table. The sun is a grapefruit sitting in the middle. Earth is a grain of sand orbiting about 2 meters away from the grapefruit. Jupiter is a pea orbiting about 10 meters away. Neptune, our outermost planet, is another pea orbiting about 60 meters away. The entire solar system on this scale fits on a small estate. Now, the nearest star, Alpha Centauri, would be another grapefruit located, and I want you to really feel this, about 40,000 kilometers away. That's the distance from here to there and back again across Earth's entire circumference. You'd have to fly from your dinner table location to the other side of the planet, and there's still just one star. Now, scale that up. The Milky Way isn't one dinner table with a few grapefruits spread across the planet. It's a disk containing about 100 to 200 billion grapefruit stars, spread across a disk about 2 million kilometers across. And Alpha Centauri, the star system closest to us, is still 40 million kilometers away on this scale. Think of it like this. The distance from Earth to the Sun is 150 million kilometers. In this scaled model, just getting to our nearest star neighbor is like traveling to the Sun and back, and then doing it about 130 more times. And that's just one star in a galaxy of billions. Now here's where your brain really breaks. You could send a spacecraft traveling faster than anything we've ever built to that nearest star, and by the time it arrived, thousands of years would have passed. Civilizations on Earth would rise and fall. Languages would change. All of history between now and the arrival would pass while you're traveling to the nearest star. And the galaxy is so vast that there are probably tens of thousands of stars between us and that destination. You're not taking a shortcut through empty space. You're weaving through a stellar field. Some of those stars might have planets, asteroids, cosmic dust. Navigation alone becomes a crisis. This is why we need to talk about the radiation problem. And this is where the cosmic environment we mentioned earlier becomes critical. As you travel through space at high velocities, you encounter particles. At 10% the speed of light, which is optimistic for any technology, we're discussing those particles. Don't just gently tap your spacecraft. They hit it with kinetic energy roughly equivalent to a nuclear explosion. Cosmic rays become weapons. Solar wind becomes a deadly hazard. Stray hydrogen atoms become bullets. Think of it like this. When a meteor hits Earth's atmosphere, it burns up from friction. You're creating friction from traveling through the interstellar medium at near-light speeds. Your spacecraft would need shielding so thick and so heavy that it would require exponentially more fuel to accelerate, which requires exponentially more fuel to accelerate that fuel. You see the problem. It's a recursive nightmare. This is the Tsiolkovsky rocket equation, first published by Konstantin Tsiolkovsky in 1903. As you try to achieve higher velocities, the fuel requirements increase exponentially. It's not a linear problem. It's exponential. This is why every rocket scientist in the 20th century understood that interstellar travel would require either revolutionary, new physics, or a fundamentally new approach to propulsion. And here's your next mind-blown moment. The fastest possible escape velocity from a black hole's event horizon is 0. Nothing escapes. But traveling at 99% the speed of light, the fastest we could theoretically go without exotic propulsion, is the closest thing to being on the edge of something impossible. You're operating at the edge of physical law, and everything becomes a problem. So the real answer to how long would it take to cross the galaxy isn't just a number. It's a statement about the fundamental architecture of the universe. The universe is big enough that it doesn't want to be crossed. Now we need to dive into something that will genuinely break your perception of reality. Relativistic effects. This is where Einstein's relativity stops being a cute physics fact and becomes absolutely critical to understanding galactic travel. Here's the brutal truth. If you tried to cross the galaxy at near light speeds using only conventional propulsion, you'd be dead long before you arrived. Your biological body can't handle the acceleration. Your organs would liquefy. Your brain would experience G-forces that would cause immediate catastrophic failure. Even if we assume some miraculous medical technology that let us survive extreme acceleration, say, suspending our bodies in liquid that prevented damage, we still hit a wall. The human body requires food, water, oxygen, and gravity. In space, gravity is gone. You're in microgravity. The human body atrophies in microgravity. Bones lose density. Muscles weaken. Blood redistributes. After a few years in microgravity, a human body is fundamentally damaged. Astronauts on the International Space Station, which is only 400 kilometers above Earth, spend about 2 hours a day exercising just to prevent catastrophic muscle and bone loss. After 6 months, they leave and require rehabilitation. A multi-year journey? The human body simply can't sustain it. Think of it like this. The human body evolved in Earth's gravitational field. We're not portable. We're environmentally dependent. We're not astronauts. We're aquatic creatures pulled out of water and asked to survive on land. Space is deeper water than we can breathe in. But here's what's fascinating. If you could solve the biological problem, maybe through genetic engineering, or uploading your consciousness to a digital substrate, or some other revolutionary technology, relativistic effects become your new prison. Let's use a specific example. Imagine you have a spacecraft that can achieve 90% the speed of light. That's absurd by current standards, but let's imagine it. You decide to travel to Andromeda, the nearest major galaxy, which is 2.5 million light-years away. From Earth's perspective, this journey takes approximately 2.8 million years. Civilizations rise and fall. The Earth's climate changes dramatically. Evolution continues. You're gone for longer than humans have existed, multiplied by 10,000. But here's the relativistic twist. From your perspective, inside that spacecraft, time passes much slower due to time dilation. At 90% the speed of light, your subjective experience of time is about 2.3 times slower than Earth time. This means, from your perspective, the journey takes about 1.2 million years. You've cut the travel time in half just by traveling really fast. But you're still experiencing over 1 million years personally. That's not better. That's still incomprehensible. But here's where it gets even more mind-bending. Imagine you're in a spacecraft traveling at 99.9% the speed of light. At this velocity, time dilation becomes extreme. A year passes for you, but 22 years pass on Earth. So let's say you travel to Andromeda at this speed. The journey, from your personal experience, might only take about 50,000 years. From your perspective, you age 50,000 years. But on Earth, 1.1 million years pass. When you arrive, Earth has changed so radically that your return journey would be to a planet you don't recognize. This is the relativistic horror. You could theoretically make a galactic journey and survive it personally by traveling at near-light speeds. But everyone you know is long dead. Billions of generations have lived and died. Civilizations have risen and collapsed multiple times. You return to an Earth that's fundamentally alien to you. Now, for crossing our own galaxy, 100,000 light years at 99.9% the speed of light, your personal journey time would be about 4,500 years. You'd age 4,500 years personally. Meanwhile, 100,000 years pass on Earth. You'd return to a world where the entire recorded history of human civilization has happened, and happened again, multiple times over. Think of it like this. If you left Earth right now on a near-light speed spacecraft bound for the other side of the galaxy, by the time you arrived, the entire history of human civilization from the invention of agriculture to today would have passed, and then repeated 30 times over. That's how much time would have elapsed on Earth. This is why interstellar travel isn't really about building a faster spaceship. It's about accepting that you're leaving behind everything. You're sacrificing your connection to Earth, to humanity, to the entire known world in exchange for traveling through space. You're functionally time traveling into the future, but only for others. And here's the final mind-blown moment of this section. If you ever tried to return to Earth from a galactic journey, you'd have essentially traveled through time. You'd be younger than everyone on Earth by tens of thousands of years. Your great-great-great-grandchildren wouldn't just be dead. Their entire civilization might be dead, replaced by countless others. This is the relativity trap. Traveling fast doesn't solve the galactic crossing problem. It just transforms it from a spatial problem into a temporal one. You're not bridging distance. You're jumping forward through time at the cost of everyone you know. So here's a question. If you can't survive a personal galactic journey, and you can't travel fast enough to bridge the distance in a reasonable time frame, what if you didn't try to do either? What if you built a ship so large that it could sustain not one human lifetime, but hundreds, thousands, or millions of human lifetimes? This is the concept of the generation ship, and it's actually one of the most serious proposals for interstellar travel that physicists consider. Instead of trying to reach a destination in one person's lifetime, you build a spacecraft that becomes a traveling world. People are born on it, live their lives on it, and die on it. Many generations pass before anyone reaches the destination. Think of it like this. Imagine taking a small city, sealing it in a pressurized bubble, and sending it through space for thousands of years. That's essentially what a generation ship would be. The first person to seriously propose this was Konstantin Tsiolkovsky, the same mathematician who created the rocket equation. In the early 1900s, he proposed massive spacecraft that could sustain human civilization indefinitely. Later, in the 1970s and 1980s, NASA and ESA scientists like Gerard O'Neill developed detailed concepts for these generation ships. Here's what a generation ship would need. First, a closed-loop ecological system. You can't pack 10,000 years of food and water for thousands of people. The spacecraft would need to be a self-contained biosphere agricultural areas, forests, water recycling systems, air recycling systems. Think of the International Space Station, but millions of times larger. Second, artificial gravity. You'd create this through rotation. A spinning spacecraft generates centrifugal force that mimics gravity. This is scientifically sound. We've never done it with humans because it's expensive, but the physics is solid. Third, energy generation. Solar panels would be useless at interstellar distances because the sun's light diminishes rapidly. A generation ship would likely need onboard nuclear reactors, multiple ones, for redundancy powering life, support systems for thousands of years. Fourth, shielding. You need protection from cosmic rays, solar radiation, and impacts from stray particles. Thick material, probably something like water, or polyethylene, or regolith from asteroids, would need to surround the habitable sections. Here's the interesting part. If you built a generation ship and sent it at the speed of current space, probes about 38,000 miles per hour, it would take about 2.6 million years to cross the galaxy. But from the perspective of the people on that ship, it's just their home. They're not traveling, they're living. They're farming, building, fighting, loving, dying, being born, creating art, music, philosophy. They're creating a civilization inside a spaceship. Think of it like this. The people on that generation ship wouldn't think of themselves as traveling. They'd think of themselves as living. They'd have their own history, their own cultures, their own languages. Thousands of generations would come and go. They might eventually forget that they were ever supposed to reach a destination. And this is where it gets philosophically profound. If a generation ship takes 2.6 million years to cross the galaxy, and the sun eventually expands into a red giant and engulfs the solar system, which will happen in about 5 billion years, does it matter? The ship isn't dependent on the sun for survival. It's self-sustaining. It could outlast Earth itself. But here's the brutal reality. Maintaining a self-sustaining biosphere in a closed spacecraft for millions of years is phenomenally difficult. One catastrophic failure in the agricultural system, one plague that wipes out the population, one cascade of system failures, and everyone dies. There's no calling for help. There's no turning back. You're committed. This is why some scientists propose what's called iterative generation ships. Multiple generation ships sent in succession. So if one fails, others might continue. It's spreading the risk. But it also means sending not thousands of people into space, but millions or billions. Think of it like this. To guarantee crossing the galaxy with generation ships, you might need to send 100 ships, each carrying thousands of people, each taking 2.6 million years to reach the destination. That's millions of people dedicating their entire lives, and millions more after them, to a journey that will outlast any nation, any language, any culture they know. This is a problem at a civilizational scale. No current nation or organization could commit to this. It would require a level of cooperation and long-term thinking that seems almost impossible in our current world. And yet, it might be the only way to actually bridge the galactic void with near-current technology. Here's a completely different way to think about crossing the galaxy. Don't send humans, send microbes. This concept is called Panspermia, and it's actually a serious scientific hypothesis studied by researchers like Chandra Wickramasinghe from the University of Buckingham and Francis Crick, yes, the guy who won the Nobel Prize for discovering DNA structure. They theorized that life might travel between worlds by hitching rides on meteorites, cosmic dust, and asteroids. Here's how it works. When an asteroid hits a planet, It can eject material into space. That material can travel through space, carrying microbes, spores, or even just organic molecules that could seed new worlds. It's not as efficient as intentional travel, but it's passive. It requires no energy, no technology, no intention. There's evidence this might actually happen. In 2020, scientists at the University of Edinburgh calculated that microbes could potentially survive the journey between stars if they were shielded inside meteorites. The cosmic radiation would be extreme, but deep inside a rock, they might survive. It's not guaranteed, but it's possible. Think of it like this. Imagine you put 1 billion bacteria in a sealed capsule and threw it into the ocean. Most would die, but some would survive and wash up on shore. Now imagine the ocean is space, and you're throwing these bacteria at different stars. If you throw enough, with enough redundancy, some might reach habitable worlds. The incredible thing about Panspermia is the timescale. If a meteorite carrying microbes somehow escaped our solar system and traveled through interstellar space at even 1% the speed of light, incredibly slow for Panspermia, it would reach the nearest star in about 400 years. And the galaxy isn't empty of flying rocks. Asteroids are constantly being ejected from solar systems by planetary collisions. Some of them might carry dormant microbes. But here's the profound part. We don't need to engineer this. It might already be happening. We don't know for certain that life on Earth originated here. The organic compounds needed for life, amino acids, nucleotides, lipids, have been found in meteorites. They've been found in space dust. The building blocks of life are everywhere. Some scientists, like Svante Arrhenius, who proposed Panspermia back in 1903, theorized that life might actually be common throughout the universe, traveling between worlds on cosmic hitchhikes. And if that's true, crossing the galaxy isn't a single journey. It's billions of tiny journeys, each one taking thousands or millions of years, each one incredibly low probability, but each one potentially seeding new worlds with life. Now here's the mind-blown moment. What if humans sent artificial microbes, genetically engineered organisms, or even simpler replicators into space deliberately? What if we created microscopic seeds designed to survive cosmic radiation, to be dormant for millions of years, and to revive and reproduce if they landed on a habitable world? This concept, sometimes called directed panspermia, would allow us to spread human biology, or at least life derived from human biology, across the galaxy without humans actually traveling. Microbes travel, they adapt, they evolve, and over millions of years, they might establish new biospheres on distant worlds. Think of it like this. Instead of sending generation ships with millions of people, you send trillions of microscopic seeds. Most don't work, but eventually, some find habitable planets and establish biospheres. Earth 2.0 emerges on a distant world, seeded by engineered microbes from Earth. Is this ethical? Is this even the right question? We don't know. But from a practical standpoint, it's the kind of approach that might actually work at a galactic scale. Because here's what's crucial to understand. Crossing the galaxy isn't a single problem. It's multiple problems with different solutions for different time scales. If you want to go fast, you need advanced propulsion. If you want to go slow, you need generation ships. If you want to go really slow, you use panspermia. Each approach trades off speed for feasibility. And the slower you go, the more feasible it becomes. Now I need to complicate everything we've discussed, because there's something about the galaxy that we barely understand, and it might completely change how galactic travel is even possible. Around 1933, astronomers noticed something strange. They measured how fast galaxies were rotating by looking at the movement of stars at different distances from the galactic center. They expected the stars far from the center to move slower than stars near the center, the same way planets far from the sun move slower than planets close to the sun. But that's not what they observed. Stars at the galactic edge were moving just as fast as stars near the center. This wasn't supposed to happen based on the known mass of the galaxy. There wasn't enough matter to hold those outer stars in orbit. The astronomer Fritz Zwicky suggested that there must be matter we can't see, dark matter. And his calculation suggested there's about 5 times more dark matter in the galaxy than visible matter. Visible matter, all the stars, planets, gas clouds, everything we can see, is only about 20% of the galaxy's mass. The other 80% is something completely invisible to every instrument we have. Think of it like this. Imagine a room full of people, but 80% of the people are invisible. You'd know they're there because of how the visible people move, but you couldn't see them. That's what the galaxy is like. There's this massive invisible scaffold holding everything together. Now, here's what's fascinating. We still don't know what dark matter is. It's one of the biggest mysteries in physics. Scientists like Vera Rubin, who won the National Medal of Science, for her dark matter research, spent decades studying this without getting a definitive answer. She died in 2016, and the mystery was still unresolved. Leading theories suggest dark matter might be WIMPs, weakly interacting massive particles, or axions, or maybe something we haven't even theorized yet. It doesn't interact with light. It barely interacts with ordinary matter. We only know it exists because of gravitational effects. And here's the mind-blown moment. Dark matter might be everywhere in the galaxy. It might form a halo around the galaxy, threading through the interstellar medium, permeating everything. And if we understood what it is, if we could somehow interact with it or harness it, it might open up entirely new possibilities for propulsion. Some speculative physicists have wondered if dark matter could be manipulated. If you could create a pocket of negative dark matter, or if you could exploit dark matter's gravitational properties in some way, you might be able to warp space differently than an Alcubierre drive would. You might find shortcuts through the galaxy. This is highly speculative. It's not established science, but it's the kind of thinking that leading physicists engage in. If dark matter is 5 times more abundant than visible matter, ignoring it when thinking about galactic scale engineering seems naive. Think of it like this. Humanity for thousands of years didn't know about electricity. We could see lightning, but we didn't understand what it was. Then we figured out electricity, and suddenly we had a new force to work with. Maybe dark matter is like that. We're aware it exists, but we don't understand it well enough to use it. But eventually, we might. And if we do, everything we've calculated about galactic crossing times might be wrong. We've been assuming you travel through space in a roughly straight line. But what if space itself could be folded? In 1935, Einstein and Nathan Rosen published a paper proposing what became known as Einstein-Rosen bridges, or wormholes. The mathematics were elegant. If you could take 2 distant points in spacetime and connect them through a tunnel, you could travel between them in far less distance. Think of it like this. Imagine a flat piece of paper with 2 dots on opposite sides. If you're an ant and you walk across the paper in a straight line, you cover the entire distance. But what if you folded the paper so the 2 dots touched? Suddenly, the distance is 0. The ant just walks across the fold. That's what a wormhole would do. It would fold spacetime so that 2 distant regions touched each other. Instead of traveling 100,000 light years, you might travel through a wormhole in days. The problem? First, you need to create the wormhole. Second, you need to keep it stable. Third, you need to navigate it. For the first problem, creation, you'd need what's called exotic matter, specifically matter with negative energy density. We've never created this. We're not even sure it's possible. It might require energies beyond anything we could ever generate. For the second problem, stability, most calculations suggest that any naturally occurring wormhole would collapse immediately under any mass trying to pass through. You'd need the exotic matter to hold it open, and you'd need massive quantities of it. Here's the numbers. Physicist Kip Thorne calculated that keeping a wormhole open would require exotic matter with the mass of Jupiter, a Jupiter mass of negative energy. That's not feasible with current physics. But here's what's interesting. Thorne's calculations were published in 1988, and since then, physicists have found ways to theoretically reduce the amount of exotic matter needed. In 2009, physicist Harold White published a paper suggesting that with the right geometry, what became known as a White-Alcubierre drive, you might need far less exotic matter. Think of it like this. Instead of moving the walls of a wormhole apart with brute force, you use the geometry itself to bend space more efficiently. It's like the difference between moving a boat through water and riding a wave. One requires strength. The other requires understanding. The problem remains that we haven't observed exotic matter. We don't know how to create it. We don't know if the physics even allows it at our scale. But mathematically, it's not contradictory to general relativity. Now here's something else that might blow your mind. Some physicists have theorized that wormholes might already exist on microscopic scales throughout spacetime. They might be constantly forming and collapsing at the Planck scale, the smallest meaningful scale in physics, about y-35 meters. If we could somehow stabilize one and enlarge it, we might create a usable wormhole. This is purely speculative, but it's the kind of thinking that's happening in theoretical physics right now. And here's the philosophical implication. If wormholes are possible, then galactic crossing times become almost irrelevant. You don't cross the galaxy through normal space. You take a shortcut through bent space. A civilization advanced enough to create wormholes would traverse the galaxy routinely. This might explain the Fermi paradox, the famous question posed by physicist Enrico Fermi in 1950. Where is everybody? If the galaxy is so vast and so old, why haven't we detected any alien civilizations? One answer is that advanced civilizations might use wormholes to navigate. They wouldn't need to broadcast radio signals across cosmic distances. They wouldn't need to send generation ships. They'd zip through space via shortcuts, staying invisible to observers like us, watching from Earth. Think of it like this. Imagine if humans invented instant teleportation. We wouldn't need to build airports anymore. We wouldn't need to maintain visible infrastructure. We'd just disappear and reappear elsewhere. An alien civilization with wormhole technology would be similarly invisible to us, even if they were nearby. This is the kind of speculation that happens when you take Einstein's equations seriously. Space and time aren't rigid. They're flexible. They can be bent, folded, warped. And if you have the right technology or the right understanding, you can exploit that flexibility. Now I want to shift the focus, because understanding galactic scale isn't just about numbers and physics. It's about something deeper. It's about your place in this vast cosmos and what that means for your life, your perspective, and your significance. You are made of star stuff. I don't mean that poetically, though Carl Sagan made it poetic. I mean it literally, chemically, actually. The carbon in your cells was forged in the heart of dying stars. The oxygen you breathe was created in stellar furnaces. The calcium in your bones, the iron in your blood, all of it came from stars that lived and died billions of years before you were born. You are a collection of ancient cosmic matter that's been arranged in a way that allows you to think about cosmic matter. You're the universe looking at itself. And on this scale, where crossing the galaxy would take 225 million years, with our fastest spacecraft, what does your individual existence mean? Here's the first part of this reckoning. It means your timeline is incomprehensibly short compared to galactic timescales. You'll live about 80 years if you're lucky. That's 0.000004% of the time it would take light to cross the galaxy. You're not just small, you're smaller than small. You're practically non-existent on cosmic timescales. But here's the second part, and this is crucial. That smallness doesn't diminish your significance. It transforms it. Think of it like this. Imagine an alien civilization observing Earth. They're watching a planet in a spiral galaxy in the middle of an incomprehensibly vast universe. They see ice ages come and go. They see continents shift. They see billions of species evolve and go extinct. And then, 300,000 years ago, which is less than a blink of an eye on cosmic scales, a new species emerges. Humans. From the alien perspective, looking through a cosmic telescope, humans might appear as a brief spark. But that spark is doing something remarkable. It's becoming conscious. It's understanding the universe. It's asking questions about galactic traversal, about dark matter, about the nature of reality itself. You are that spark. Your consciousness, your ability to wonder, to question, to understand, that's extraordinarily rare. The universe, as far as we know, doesn't have another example of a species contemplating cosmic distances. Not yet. Now, here's something that should reframe your entire perspective. The fact that you're asking, how long would it take to cross the galaxy, means you're part of a species capable of building devices to leave the solar system. Voyager 1 is a machine made by humans, and it's currently the farthest human artifact from Earth. It's the embodiment of human curiosity and ambition. In 40 years, we've sent a spacecraft 14 billion miles away. In less than a century, we've gone from first powered flight to landing on the moon to robots exploring Mars. Do you understand how rapid that progression is? If this rate of technological acceleration continues, and yes, it has slowed slightly from the 1960s peak, but it's still accelerating, then within centuries, maybe even within a few thousand years, humanity might develop technologies we currently think are impossible. Think about it. 500 years ago, the fastest humans could travel was maybe 20 miles per hour on horseback. Today, we travel at 25,000 miles per hour on spacecraft. In another 500 years, we might be traveling at 25% the speed of light. Or we might have solved the wormhole problem. Or we might have discovered something completely different that makes all our current thinking obsolete. This is the nature of exponential technological change. Each generation's impossible becomes the next generation's normal. And here's where this gets personal. You live at an absolutely unique moment in human history. You're the first generation with access to the entire sum of human knowledge, your fingertips. You can learn about galactic distances, about physics, about the history of the universe, instantly. Your ancestors couldn't do that. You're also the generation that's watching the most rapid technological changes in human history. AI, CRISPR, gene editing, quantum computing, space travel becoming commercial. These aren't just changes. They're the kinds of foundational shifts that only happen once per 1,000 years. Your lifetime might be the crucial moment where humanity goes from being confined to Earth to becoming spacefaring. Or it might be the moment where we make irreversible mistakes. Or it might be both. You're living through one of the most important centuries in human history, and most people don't realize it. Here's what I want you to feel right now. You are insignificant on cosmic timescales, but not in cosmic significance. You're a conscious being in an unconscious universe. You're asking questions that almost certainly no other species in this galaxy has asked. You're part of something extraordinary. And when you think about crossing the galaxy, when you contemplate that 225 million year journey, you're not just thinking about physics. You're thinking about the future of your species, about what humans might become, about the possibility that your descendants might one day reach the other side of the galaxy. That's not small, that's profoundly significant. Now let's connect everything we've discussed to one of the greatest mysteries in science, the Fermi paradox. In 1950, physicist Enrico Fermi sat down to lunch with colleagues and asked a deceptively simple question. Where is everybody? Think about it. The galaxy contains an estimated 100 to 200 billion stars. Most of those stars probably have planets. Even if just a tiny fraction of those planets harbor life, we should be seeing civilizations everywhere. We should be detecting radio signals. We should see massive engineering projects. We should see evidence of alien spacecraft. But we don't. The universe appears profoundly, eerily silent. This is the Fermi paradox. There are lots of proposed solutions. Let me go through the most interesting ones, and I want you to notice how everything we've discussed today connects to these solutions. The first is called the Great Filter. Maybe there's a barrier, a great filter, that prevents civilizations from spreading across the galaxy. This barrier could be early. Perhaps intelligent life is incredibly rare, and the odds of any civilization achieving technological sophistication are vanishingly small. Or it could be late. Perhaps civilizations self-destruct. Perhaps when any species reaches a certain technological level, they inevitably destroy themselves through war, environmental collapse, or some other catastrophe. The implication is sobering. If the Great Filter is in front of us, then humanity is approaching the filter. If the Great Filter is behind us, then we've already passed it, and we might be among the oldest civilizations in the galaxy. The second solution is time. The universe is 13.8 billion years old. The galaxy formed about 13 billion years ago. Early civilizations might have risen and fallen. There might have been dozens of spacefaring civilizations over galactic history, but they've all disappeared. And the odds of multiple civilizations existing at the same time, in the same galaxy, at the same moment in cosmic history, are tiny. Think of it like this. Imagine you visit an ancient city that was once bustling with millions of people. Now it's empty ruins. If you only visit once, for 1 hour, you won't see any evidence of the current civilization. You might conclude it's abandoned, but civilizations come and go. The odds of your visit coinciding with the moment when multiple civilizations exist simultaneously are slim. The third solution, and this connects directly to our discussion of galactic crossing times, is that spacefaring civilizations are incredibly isolated. They don't spread across the galaxy the way science fiction imagines. They don't colonize nearby stars routinely. Why? Because of the problem we've spent this entire video exploring. The galaxy is so vast that crossing it requires timescales of hundreds of thousands to millions of years. Maybe advanced civilizations simply accept that they're isolated. Maybe they focus on their own solar system. Maybe they develop virtual realities so elaborate that the physical universe becomes less important. Maybe they upload their consciousnesses into digital systems and abandon physical space travel entirely. If this is true, then the Fermi paradox's resolution is simple. Everyone's alone. Every civilization thinks they're unique. Every species develops in isolation. Occasionally, they might send probes or Panspermia seeds across the galaxy, but they never physically travel between stars. They never establish galactic civilizations. They're forever confined to their local region of space. Think of it like this. Imagine if the internet existed, but data could only travel between cities at the speed of a horse. You could theoretically communicate between New York and Tokyo, but the latency would be measured in months or years. You'd essentially be isolated. You'd develop local communities. You might occasionally send historical records to other communities, but you wouldn't have real-time interaction. You wouldn't have a global civilization. That might be what the galaxy is like. Billions of isolated civilizations, separated not by technology, but by distance and time. But here's the fourth solution, and this is where our discussion of wormholes and exotic physics comes back. Maybe advanced civilizations do solve these problems. Maybe they figure out wormholes or faster-than-light travel. Maybe they do spread across the galaxy. And maybe the reason we don't see them is because we're not advanced enough to detect them. If a civilization is millions of years older than us, they'd be operating at technological and conceptual levels so far beyond us that we wouldn't recognize their presence even if they were nearby. Their technology would look like magic to us. Their communication would be incomprehensible. Their engineering projects would blend into the cosmic background. Carl Sagan made a great point. Any sufficiently advanced technology is indistinguishable from magic. If a Type 2 civilization, a civilization capable of harnessing the entire energy output of their star wanted to hide from us, they could. We'd be looking at the wrong scales, the wrong wavelengths, the wrong dimensions of reality. So the Fermi paradox might not be saying, "Where is everybody?" It might be saying, "We're so far below the detection threshold of advanced civilizations that we're literally invisible to them." This connects to our earlier discussion of panspermia and directed panspermia. An advanced civilization might have seeded this galaxy with microorganisms, spread life across worlds through passive panspermia, and never needed to physically visit. They'd be the architects of life on billions of worlds, but we'd never know because they're operating on scales we can't perceive. Here's the mind-blown moment. One of those seeded worlds might have been Earth. The amino acids found in meteorites? Maybe they weren't random cosmic accidents. Maybe they were directed. Maybe life on Earth is a branch of a galactic tree deliberately cultivated by a civilization so ancient and so advanced that they've been forgotten even by the universe itself. We don't know. But the vastness of the galaxy, combined with the isolation imposed by galactic distances, makes this not just possible, but perhaps probable. Let me paint a picture of what the next 10,000 years might look like for humanity, assuming we don't self-destruct and assuming we continue advancing technologically at even a modest exponential rate. In 500 years, I expect we'll have permanent settlements on Mars, Venus, and the moons of Jupiter. We might have visited and surveyed the nearest star systems with unmanned probes. We might have discovered the nature of dark matter and begun theoretical work on advanced propulsion. In 1,000 years, assuming technological acceleration continues, we might have fusion-driven spacecraft achieving 10 to 20% the speed of light. We might have launched the first-generation ships toward nearby star systems. We might have genetically modified humans capable of surviving radiation and cosmic environments far more effectively than current humans. We might have developed artificial intelligences that are dramatically more capable than biological humans at solving engineering problems. In 5,000 years, we might have established the first settlements around nearby stars, Alpha Centauri, Sirius, Altair. We might have begun systematic exploration of the local neighborhood of stars within 100 light years of Earth. The generation ships might be landing, establishing colonies, and beginning the process of adapting to alien worlds. We might have discovered wormhole physics and begun constructing small-scale experimental wormholes. In 10,000 years, the picture becomes more speculative, but conceivable. Humanity might span dozens of star systems. We might be a multi-system civilization. We might have spread life across entire regions of the galaxy through directed panspermia. We might have cracked the mysteries of advanced propulsion and begun the methodical process of crossing toward the galactic center. We might have encountered or contacted alien civilizations. Or we might still be alone, but confident in the knowledge that we're not because we're hiding or out of communication range. Think about this historically. 10,000 years ago, humans invented agriculture. We went from nomadic hunter-gatherers to settled civilization. That single technology changed everything. It led to cities, writing, governance, science, everything that makes modern civilization possible. It's been 10,000 years, and we've gone from agricultural settlements to nuclear-powered spacecraft circling other planets. Now imagine another 10,000 years of that kind of exponential change. The difference between us and our descendants might be as vast as the difference between ancient Sumerians and modern humans. We might not even recognize them as human. They might be biological, digital, hybrid, or something we can't currently conceptualize. And here's what's crucial. This isn't guaranteed. Technology doesn't automatically continue advancing. Civilizations collapse, resources deplete. Wars and chaos can interrupt progress for centuries. But assuming we navigate the dangerous transitions artificial intelligence, climate change, nuclear weapons, pandemic disease that we're currently facing, continuing technological development seems likely. And if we do continue developing, crossing the galaxy becomes not a question of if but when. The timescale might be millions of years. It might be billions of years. But the vast majority of the history of the universe is ahead of us. We have time. Think of it like this. Humanity is currently a toddler species. We've only had fire for about 1 million years. We've only had electricity for about 150 years. We've only had the internet for 30 years. We're infants. We're making mistakes, breaking things, not understanding the consequences of our actions. But we're learning at an extraordinary rate. Imagine a toddler asking, "How long would it take me to walk to the other side of the continent?" The answer isn't just about distance. It's about development. A toddler can't walk across a continent because they haven't developed the physical capacity, but an adult can. In a few years, that toddler will develop the capacity. Humanity is in the developmental stage. We're not capable of crossing the galaxy yet, but in a few thousand years, we might be developed enough to do it. Not because the physics changes, but because we change. We develop new capacities. And here's the profound part. This development might fundamentally alter our understanding of what it means to be human. If we spread across the galaxy, different branches of humanity on different worlds will evolve differently. We might diverge into different species. We might form a federation of sentient beings that includes digital minds, genetically modified humans, artificial intelligences, and post-biological entities that started as human but transformed into something new. We might become a Kardashev Type 2 civilization, a civilization capable of harvesting the entire energy output of multiple stars. We might engage in stellar engineering on scales we currently can't conceive. We might reshape the galaxy over millions of years. Or we might remain local, confined to the solar system, focused on perfecting our own world and consciousness. We might decide that the galaxy is too vast and too empty to bother with. We might achieve technological transcendence and leave physical reality altogether, existing in digital universes inside computers, more complex than our biology could ever support. What I'm saying is, the future of humanity isn't determined. The future is a landscape of possibility. And how humans navigate that landscape will determine whether we ever cross the galaxy and how long it takes us to do it. But one thing is certain. The knowledge that the galaxy exists, that it spans 100,000 light years, that it contains hundreds of billions of worlds, that knowledge changes us. It changes our perspective. It makes us understand that we're part of something vastly larger than ourselves. And that changed understanding? That's the first step toward being a galactic civilization. All right, so we've gone deep. We've covered physics, relativity, generation ships, wormholes, dark matter, the Fermi paradox, and the future of humanity. Now let me give you the real answer to the question we started with. How long would it really take us to cross our galaxy? The surface answer is simple. With current technology, 225 million years. With advanced propulsion, maybe 300,000 years with generation ships. With theoretical physics like wormholes, potentially years or decades if we could create stable shortcuts. But the real answer is more complex, and more beautiful, and more significant than any number. The real answer is, it depends on who us is, what cross means, and what timeline we're operating on. If us is humans as we currently exist, biological, needing Earth gravity, needing oxygen, needing stable temperatures, then we can't cross the galaxy. We can't survive it. Our biology won't allow it. We could potentially send generation ships with evolved versions of ourselves, but those people wouldn't be us in the way we're us. They'd be different. They'd be adapted to their journey. If cross means physically traveling from one edge to the opposite edge in a straight line through normal space, then we're talking about millions of years minimum with any technology we can currently conceive of. But if cross means gradually spreading, colonizing, adapting, and establishing civilizations across the galactic expanse, then we might already be crossing it. Every generation ship we send, every Panspermia seed we launch, Every scientific breakthrough that moves us closer to advanced propulsion, all of that is crossing the galaxy, just in slow motion. We're not crossing it in a single journey. We're crossing it through generations, through exponential expansion, through the accumulation of small steps into civilizational achievement. Think of it like this. When Europeans began colonizing the Americas, it took about 500 years to fully cross and colonize the continents. That seemed like an enormous timeline at the time, but in the context of human history, it was incredibly fast. What took 500 years was expanding human civilization across an entirely new world. Now scale that up. Crossing the galaxy might take 500,000 years or 5 million years. But in the context of cosmic history, that would be incredibly fast. We'd be expanding human civilization across an entire galactic region in what amounts to a cosmic blink of an eye. And here's the profound insight that should reshape your thinking about this entire topic. Time is relative to the observer. From the perspective of someone on Earth right now, 225 million years is unimaginably long. It's longer than we can emotionally comprehend. It dwarfs all of human history, all recorded civilization, everything we've accomplished. But from the perspective of the universe itself, from the perspective of someone living in the year 1 trillion looking back at the period when humanity spread across the galaxy, it would seem like it happened recently. It would be recent history. It would be the equivalent of us talking about the fall of Rome or the development of agriculture. And from the perspective of entropy itself, from the perspective of thermodynamics and the slow heat death of the universe, 225 million years is almost instantaneous. The universe will last for trillions of years. By that timeline, humanity crossing the galaxy in a few million years would be extraordinarily fast. So the answer to how long depends entirely on your reference point. Here's what I want you to take away from this video. First, you now understand something that very few people understand. You can visualize galactic scale, at least intellectually. You know that 100,000 light years is mind-shatteringly vast. You know that crossing it would take timescales that dwarf human history. And you know why. You understand the physics. Second, you understand that the barriers to galactic crossing aren't primarily technological obstacles, though they're significant. The barriers are conceptual and temporal. Humanity would need to maintain commitment across millions of years. Different branches of humanity would need to survive and adapt. Resources would need to be sustained across generations, spanning longer than civilization has existed. Third, you understand that crossing the galaxy isn't really possible for humans as individuals. It's only possible for civilization, for species, for the long-term continuation and evolution of humanity itself. And fourth and most importantly, you understand that you're part of that process. Right now, today, your existence, your consciousness, your capacity to ask questions about cosmic scales, all of that is the foundation for whatever humanity becomes in the next millions of years. Every scientist working on propulsion technology, every person who appreciates the wonder of the cosmos, every person who chooses to educate themselves about these vast distances and possibilities, all of that is moving humanity toward being a galactic civilization. You're part of it just by understanding it, just by wondering about it. Visual, montage of images, stars, galaxies, scientific achievements, human exploration, DNA, consciousness, and finally, back to Earth. Here's the final thought, and I want you to feel this deeply. We live in an era where crossing the galaxy has moved from fantasy to possibility. We have the theoretical physics in place. We have the beginnings of the technology. We have the understanding. What we're missing is time and intention. The universe is 13.8 billion years old. Humanity is 300,000 years old. Civilization is 10,000 years old. Modern science is 500 years old. And space travel is 70 years old. If this exponential progression continues, at some point in the future centuries from now, or millennia from now, humanity will achieve the knowledge and ability to truly cross the galaxy, not as individuals, not as a single mission, but as a civilization spanning millions of worlds, connected by wormholes or advanced communication networks, united by shared origin, gradually expanding across the galactic expanse. And when future historians look back at this era, at this moment in cosmic time, they'll recognize that this was when it started. This was when humanity began asking the right questions. This was when we started understanding what we'd need to become to be a galactic species. You're living through the beginning. You're part of the foundation upon which a galactic civilization will eventually be built. And that is profoundly significant. That gives your life meaning in the context of something so vast, it's incomprehensible. You're not just a person living on Earth in 2026. You're a conscious being living at the threshold of your species' greatest expansion. You're part of something cosmic. So the answer to how long would it really take to cross our galaxy is, it depends on what we become, and we haven't finished becoming yet.